Hey, it's Papa. This is the third video in the Plate Tectonics History of Georgia and the Southeast series. We talked about the rifting of Rodinia in the first one, supercontinent Rodinia. I talked a little bit about the physiographic and the geologic provinces of Georgia on the second one. Now we're going to talk more about the rifting of Rodinia, but mainly we're also going to talk about the Rift-to-Drift stratigraphic sequence and the Cambrian explosion. So here we go. Okay, you can tell this is the eastern United States here, and this is what it looked like right after Rodinia rifted. You know, Rodinia, the supercontinent, rifted between about 750 million years ago and 550 million years ago. And when it rifted, it created several features. First of all, an ocean was created off the coast of North America and other continents. Between North America and the other continents. This is that ocean. I think they call it the Apatus Ocean or something like this. Just the proto-Atlantic Ocean. Another thing that the rifting created, that was a total, complete rift over here. The next thing that it created was like a semi-rift where a hunk of this land crust broke loose and drifted out off the coast of North America, but it didn't create a rift here. This was just a space. It didn't get wide enough to create a rift. The main rift was over here. And then also, all along here, all up and down the eastern United States, it created what we call rift grabens or rift basins. Grabens is the German word. It just means basins. These are where because of the rifting process, the land crust thinned and stretched and cracked, and one piece dropped down relative to another piece and created these basins. So this is the rifted margin of North America after Rodinia rifted. And so all up and down the eastern United States, you've got these rift grabens and lava flows. Hey, now, we talked about earlier that the Great Smoky Mountains National Park is a great place to see rift grabens because it is a giant rift grabens with the cool rocks that are in there. But also examples of the lava that was produced are the Catoctin Formation in Virginia, which is basalt and rhyolite lava flows that help do the rifting of Rodinia. And then in North Carolina, you have the you've got the Crossnor plutons and the Mount Rogers and the Grandfather Mountain formations that represent lava flows that occurred, and they didn't result in full rifting, whereas the Catoctin basalt and rhyolite flows did. But the main thing is all up and down the eastern United States, you've got these old rift grabens and lava flows. And part of the fun is just to go find them. Okay, so and like I said before, this whole thing is just a rifted hunk of land crust that rifted off and separated. Now, this was underwater. All this was underwater. It was a shallow continental shelf. This piece of crust was underwater, and this was underwater, shallow water. And now I have to tell you something about what Rodinia did as it was rifting. Rodinia began its existence in the southern hemisphere down maybe 50 degrees south latitude where it's cold. There were glaciers down there, and when it started rifting, the glaciers dumped a bunch of glacial till all around it. But the main point is it started moving north, which, as we know, with plate tectonics, that does happen. Continents, supercontinents, and regular continents move all over the globe. It happened very slow about the speed with which fingernails grow. And I'll give you an example. Okay, see that middle finger right there? See that brown spot on it? Well, about 1 month ago, I chopped my finger with an axe, and that brown spot was right up there at the cuticle. In 1 month, it's grown from the cuticle out that far, maybe 3/8 of an inch, maybe 1/4 of an inch, something like that. That's how fast plate tectonics activities occur. Anyway, as Rodinia was rifting, it was moving north, and it moved into warmer latitudes, closer to the equator, and that did something wonderful. Oh, also, what happened? Rodinia moved north, and also the rifted margin of the continents that were formed, the North American continent, sank. When a supercontinent rifts, all the pieces of the continent pieces that result, they begin to sink, and the ocean begins to transgress or come up. The land sinks and the ocean rises, and that is significant too. So what happened was, this was shallow water, and now that Rodinia was in a warmer latitude, it was warm water, and maybe 300-400 feet max depth. The sunlight could penetrate down into that depth, and lo and behold, life burst forth in the Cambrian explosion. Well, here's what happened. As the land sinks, let me show you this. This will help. As the sea is advancing, this is the continent. Here's the ocean. This is a side view. The sea is advancing. Well, the first thing you have is you've got all these sandy beaches and coastal plains on the edge of the continent where the sea is. But as the sea rises, mud from out deeper begins to come up and cover the sand, and the sand beach migrates up the hill. And as the sea continues to transgress or rise, the ocean gets deeper where the mud was, and the water's clear and warm and shallow, so sea creatures can develop. Sea creatures that use calcium, clams, oysters, and coral reefs, and that's exactly what happened. For the first time ever, about between 550 million years ago and about 530 million years ago, the conditions were perfect for the beginning of life in the sea, or the explosion of life in the sea. It had already been there. All along in here was the shallow continental shelf, and there was a lot of calcium in the water. Where did that calcium come from? Well, Rodinia, as Rodinia was put together, many volcanoes erupted. That's just part of the continent building process. And those volcanoes erupted basalt, lava, and gabbro magma, which is chock full of calcium. And that calcium, because back in that time, there were no plants at all on the land, so erosion was tremendous, and all this calcium was washed down into the ocean and kept being washed down in these shallow seas. And these creatures had evolved to the point where they could take that calcium, mix it with carbon dioxide that came from the atmosphere, and make all these shells. And the Cambrian explosion occurred. You've probably heard of the Murphy Marble Belt, which is in the western Blue Ridge geologic province. That's when the Murphy Marble Belt formed. It wasn't a small, narrow belt back then. It was a flat, wide shelf of coral reefs and sea creatures that was in this area here that developed on top of these grabens in this beautiful shallow water. Later on, it got mashed and crashed and folded into the western Blue Ridge province as a long, twisty, narrow belt of marble. Started out as limestone, but the metamorphism associated with crashing it and smashing it and folding it turned it into beautiful marble, and I'll show you some of that in the next video. Maybe this one we'll see. Okay, not only that, but out here, limestone, sandstone first, then mud, and then limestone developed in this area, all up and down the coast of the North America. And one great example, remember I said the sand beaches were the first thing to form and make a layer of sand? Well, that layer of sand turned into sandstone and quartzite, which is the metamorphic version of sand. And where can you see it? The most fantastic example of those ancient beaches of Cambrian time are located, once again, just west of Great Smoky Mountains National Park. If you go to Townsend, Tennessee, there's a mountain called Chihowie Mountain, just to the west, to the northwest of Townsend, and it runs all up and down North Carolina, Tennessee. Actually, it's in Tennessee. It goes way up north. I don't know how, probably through up into Virginia. Yeah, it definitely goes up through Virginia because it forms the mountain that the Shenandoah National Park is located on, and it comes all the way down into Georgia. If you go up to Townsend area and you look for the Foothills Parkway, get on the Foothills Parkway and drive it, you're on top of Chihowie Mountain. You're on top of the former sand beaches that existed as the continents were sinking after Rodinia rifted. And you can go, if you travel that Foothills Parkway, magnificent views. When you get to the end, you can walk up a tower, and all around you on that tower is the remains of those ancient beaches, and they've got these little worm tracks in them, scolithus worm tracks in them. It's super cool. Okay, so that was that part. If you also, if you go to our Great Valley here in Georgia, and the Great Valley goes all the way up the eastern United States, it's chock full of limestone, and a lot of that limestone came during this Cambrian explosion time. It's called the Knox limestone. So anyway, you can go Townsend, Tennessee. The Knox limestone is all over Townsend, Tennessee. If you go to Cartersville, Georgia, just Chatsworth, Georgia is a good place to see it. Chatsworth. And our Valley and Ridge province of Georgia, you're driving all over. When you're in the valleys, you're driving over first Cambrian, early Cambrian limestone, then later limestone. But it's beautiful limestone. Okay, at the same time, that Murphy marble limestone was forming here. Out here, you had the rest of the continental shelf, and then it dropped off into a steep continental slope, and then eventually down to the deeper ocean. And you had a whole set of rocks formed there that are called the Alligator Ash Tallulah Falls Formation. And if you go, those were the deeper rocks that formed deeper than the continental shelf. It's called the continental slope, and then the deeper basin, and they are turbidites, which you probably remember from our first video, that turbidites are rocks formed when sand and pebbles roll down underwater slopes and get all mixed up. Well, and also if you go to Tallulah Falls here in Georgia, all that rock there is from that continental slope and continental deep basin, mostly the continental slope way out here. So those are those rocks, and that's how they form. Let me see if I need to tell you anything else about this. Oh, and the process by which, after a supercontinent rifts and it begins to sink, which always happens, the pieces, the continent pieces, their edges begin to sink. And you get first sand, a layer of sand, then you get a layer of mud, and then you get a layer of limestone. That is called the Rift-to-Drift sequence, stratigraphic sequence. And it not only happened here in the east coast of North America, it happened all over the world. It happened all over the United States. An example is if you go out to Bighorn Mountain the Bighorn Mountains in Wyoming. You've just got layer upon layer, and one of the lowest layers is a sandstone called the Flathead Sandstone, and it runs over to Idaho and other places. That is the same as Chilhowie. It's those old ancient beaches. And then above the Flathead Sandstone, you've got something, I think it's the Gallatin Formation, which is the muds that turned into that came on top of the sands, and those muds turned into shale and then later slate. And then on top of that, you have let's see. You have a layer of limestone. I think that's the Gallatin Formation. The mud is called the Gros Ventre Formation, I believe it is. But you have the Gallatin Formation, which is the limestone, and it's just the same as the Murphy. Well, really just the same as the limestone that formed here after as the ocean rose. One of the greatest examples of fossils from this Cambrian explosion is called the Burgess Shale, which is located high in the Rocky Mountains of British Columbia. With pressure, the shale, metamorphic pressure, turned the shale into slate, which has these thin, easily broken apart layers. And Dr. Wolcott of the USGS Survey, U.S. Geological Survey, back in the early 1900s, maybe before then, was riding his horse up through there in a trail and found these fossils. He began splitting these shales, and he found hundreds and hundreds of examples of many species of ancient Cambrian creatures that lived, and even the soft body parts were preserved. And that's probably, the Burgess Shale is probably the most fantastic fossil find in the world today. Okay, what else? I think that's all for now. I'll show you some of the rocks. Okay, as this is from the book. And as the continent edge sunk, you had these sand beaches which turned into sandstone. Now, this is not Cambrian sandstone. This came later during the Allegheny orogeny, but it's the same thing. And a lot of that sandstone, it's sand grains that are glued together with, it could be iron that's gluing together, it could be calcium that's gluing them together, it could be silicon that's gluing them together, but that's that layer of sandstone, the Chilhowie sandstone, Flathead sandstone, and other sandstones all over the United States. Then you got shale. And this is Conasauga Shale, which this is actually Cambrian shale. This would have come on top of the sandstone. It's soft. You can scratch it with your fingernail. And it's red instead of black. Other shales, like this shale, which is from Mississippian time, is black. And you can see a bit of a fossil in there. This one's not. It's red. And why is it red? Number one, it has a lot of iron in it. And it must have spent some of its life in dry stream beds before it was washed down into the ocean to form the shale. And also, there wasn't a lot of organic material on the land back then, so it's going to be red instead of black. Okay, and then finally, let's see if we can find some limestone. So first you get the sandstone, then you get the shale. Here we go, limestone. Limestone, which is it starts off as calcium-rich mud. And the calcium comes from all the sea creatures and coral reefs, shellfish that have died and their calcium-rich bodies settle down and get mashed. It's mostly gray, light gray, dark gray. It can be even black. And the dolomite version of it, which is limestone that's had magnesium added, can be kind of white or light gray. You see those light-colored streaks? Those are calcium carbonates, veins of calcium carbonate in there. And limestone is soft. If you can scratch it with a knife, if you scrape off a powder and put it in vinegar, it will fizz. There's another example of a different kind of limestone, but it's all limestone. These are limestone. There's a limestone. It's not yet limestone. It comes from the Clinchfield, Georgia quarry, and it's fairly young stuff. It maybe was laid down in Cretaceous time or even after, which Cretaceous was about 150 million to 65 million years ago, probably after that. And then here's some dolomite, which is kind of grayish or whitish. So that's the story with the rift-to-drift sequence after Rodinia rifted, and the different geologic features that were created by that process. Next time we're going to talk about, we've been talking about how the supercontinent Rodinia is rifted apart. Next time we're going to start talking about how the new supercontinent first began to come together. Alrighty, Papa out.